Welcome to today's lecture on quantum computing. Over this hour, we are going to explore two fundamental modules that form the heart of quantum computing, the qubits and quantum gates. These concepts might seem strange at first because they operate according to the rules of quantum mechanics, which are very different from everyday physics we are used to. But don't worry, we'll break everything down step by step using analogies and examples you can relate to. This is your Professor T. Farid Muhammad. Today's journey will take us from understanding that qubits is all the way to building simple quantum circuits. We will discover why quantum computers are so powerful, yet so difficult to build. You will learn about some of the strangest phenomena in physics, including superposition and entanglement, concepts that even Albert Einstein found hard to believe. These are not just theoretical ideas, they are the foundation of technologies being developed right now and that could change our world. By the end of this lecture, you'll have a solid understanding of how quantum computers work at a fundamental level. You will be able to explain these concepts to others, and you will understand why scientists and engineers around the world are racing to build better quantum computers. So let's dive into the fascinating world of quantum computing, starting with the most basic question: what exactly is a qubit? So let's start with something familiar, the bits in your computer. As we discussed earlier, every piece of digital information you have ever seen, every text message, every photo, every video is stored as a series of bits. Each bit is like a tiny light switch that can be either on or off, representing 1 or 0. When you have 8 bits together, you get a byte, which can represent a single letter or number. Your phone might have 128 gigabytes of storage, which means 128 billion of these switches, each holding one definite value at any given time. Now, quantum bits or qubits work completely differently. Instead of being definitely on or off, a qubit can exist in a state of superposition, meaning it is somehow both 0 and 1 at the same time. I know this sounds impossible, but it is a real phenomenon in quantum mechanics. Think of it like a coin spinning in the air, as we have discussed earlier. While it is spinning, it is not heads or tails, it is both. Similarly, a qubit is not just uncertain or unknown, it genuinely exists in both states simultaneously until we measure it. This is fundamentally different from just not knowing which state something is in. This difference in reality, it might seem subtle, but it is revolutionary. A regular bit gives you one piece of information, but a qubit can explore multiple possibilities at once. When you have multiple qubits working together, this advantage grows exponentially. Two regular bits can be one in one or four of four states at a time: 0, 0, 0, 1, 1, 0, or 1, 1. But two qubits can be all in all four states simultaneously. This is a source of quantum computing incredible potential power, and it's why scientists are so excited about this technology. So let me outline the specific learning objectives of today's lecture before I continue. First, we just have explored the qubits and how it is fundamentally different, or it differs from the bits in your laptop or smartphone. You will also learn how to visualize these quantum states using the geometric model called the Bloch sphere, which helps us understand what is happening inside a quantum computer. We will also tackle one of the most mind-bending concepts in physics, superposition, which means existing in multiple states simultaneously. So think of this in a way that a regular bit is like choosing chocolate or vanilla. A qubit is like having both flavors at once until you take a bite. So let's continue. Understanding qubits becomes much easier when we can visualize them. And that is where the Bloch sphere, BLOCH, comes in. Named after physicist Felix Bloch. This is a three-dimensional sphere where every single point on the surface represents a possible state of a qubit. Imagine holding a globe in your hands. The north pole of this sphere represents the qubit being definitely in state 0, while the south pole represents it being definitely in state 1. These are the only states a classical bit can have, but a qubit can be anywhere on this entire sphere. The equator of the Bloch sphere is particularly interesting because it represents states of perfect superposition where the qubit is equally likely to be measured as 0 or 1. Different points along the equator differ in something called phase, which is like the difference between waves that peak at different times. The front of equator represent an equal superposition with positive phase. The back represents an equal superposition with negative phase. And the side represents superpositions that with imaginary phase. Don't worry too much about the math of imaginary numbers. Just understand that different points represent different ways of being in superposition. What makes this Bloch sphere so powerful is that it lets us visualize quantum operations geometrically. When we apply a quantum gate to a qubit, we can think of it as rotating the point on the sphere. This visual model helps us understand complex quantum operations without getting lost in abstract mathematics. As we learn about different quantum gates later in this lecture, we'll keep referring back to the sphere to see how each gate moves our qubit state to a new location. Now let's tackle one of the weirdest and most important concepts in quantum mechanics, that is superposition. In our everyday experience, things are in one definite state. A light is either on or off, a door is either open or closed, and you are either awake or asleep. But in the quantum world, particles can exist in multiple states simultaneously. A qubit in superposition is not just probably 0 or probably 1. It generally exists as both 0 and 1 at the same time until we measure it. Let me give you some analogies to help wrap your mind around this. You might have heard, and obviously we have discussed that earlier, of Schrodinger's cat. A thought experiment where the cat in the box is both alive and dead until you open the box and look. That is the collapsing of a state to figure out what's your end result. While that's a bit extreme, it captures the essence of superposition. A better everyday analogy is a coin spinning in the air. While it is spinning, it is not heads or tails, but both. It's technically a coin in the air. Or think of a wave in the ocean. It exists along with its entire path simultaneously, not as just one point. These are not perfect analogies because quantum superposition is truly unique, but they give you a sense of what's happening. Different types of superposition are possible. A balanced superposition means a qubit has exactly a 50% of chance of being measured as 0 and 50% of chance of being measured as 1. So probability comes into play. But we can also create biased superposition like 75% chance of 0 and 25% chance of 1, or any other combination as you want. There is also something called phase difference, which affects how quantum states interfere with each other. This is crucial for quantum algorithms, which use interference to amplify correct answers and cancel out the wrong ones. Superposition is what gives quantum computers this parallel processing power. So the importance is this is not just we don't know which, it is genuinely both when we are looking at this example. What happens when we measure? So in reality, the measurement process. So here's where quantum mechanics get really strange. The act of measurement fundamentally changes the system. Before you measure a qubit, it exists in superposition genuinely in multiple states at once. But the moment you measure it, the superposition collapses and the qubit becomes definitely 0 or 1. Definitely 1. You never see a qubit in between because the measurement itself forces it to choose. This is not the limitation of your measuring devices, it is a fundamental feature of quantum mechanics. Let's walk through this process step by step. Imagine you have a qubit in a perfectly balanced superposition, like an equal mixed state we discussed earlier. This qubit is genuinely both 0 and 1 before measurement. Now you measure it, what happens? And we have done this in our previous discussions, this sort of experimentation. The superposition collapses and you get either 0 or 1 as your result. In this case, with 50% probability of each outcome, once you have measured it and gotten, say, 0, the qubit is now definitely 0. If you immediately measure it again without doing anything else to it, you will get 0 again because the superposition has already collapsed. This measurement problem has profound implications. First, it means that measuring a quantum state destroys the very quantum properties you might want to use. This is why quantum computing is so tricky. You need to do all your calculations in superposition and only measure at the very end. Second, it means quantum processes are fundamentally probabilistic. If you prepare identical qubits in the same superposition and measure them, you will get different results each time. You can only predict the probabilities, not individual outcomes. This randomness is not due to hidden information, it is built into the fabric of reality according to the quantum mechanics. So if a qubit is 50-50 balanced, you will get a 0 half and half of the time and 1 half the time over many measurements. So working with multiple qubits, when we move from single qubits to multiple qubits, the power of quantum computing really starts to become apparent. Let us start simple. One qubit can be in two possible states when measured, 0 or 1. But what about two qubits? With two classical bits, you could have four possible combinations as mentioned earlier, 0, 0, 0, 1, 1, 0, or 1, 1. But you can only be in one of those states at any given time. However, two qubits in superposition can be in all four of these states simultaneously. This is where quantum parallelism begins. As we add more qubits, the number of states that can exist in superposition grows exponentially. 3 qubits can represent 8 states at once, and those are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and or 1, 1, 1. 4 qubits can represent 16 states. 10 qubits can represent 1024 states simultaneously. The pattern is clear. N qubits can represent 2 to the power n states. This exponential growth is astonishing. By the time you get to 300 qubits, you could represent more states than there are atoms in the observable universe, and all of these states could exist in superposition at the same time. This exponential scaling is why quantum computers are potentially so powerful for certain problems. A classical computer solving a problem with a trillion possibilities would need to check them at one at a time, all of them at one at a time, or use clever shortcuts. But quantum computer with about 40 qubits could hold all trillion possibilities in superposition simultaneously. Of course, there are complications. We can't just look at all these answers because measurement collapses the superposition. Quantum algorithms must be cleverly designed to amplify the correct answer and suppress wrong answers through quantum interference. But the potential is enormous, and it is all about the foundation of multiple qubits in superposition. When we want to describe a system of multiple qubits, we need a way to combine individual qubit states into a complete description. This process is called taking the tensor product through, though don't worry too much about the mathematical name. The concept is straightforward. Essentially, when you combine two qubits, you multiply out all the possibilities to see whether the state, whether what states the combined system can be in. Let us work through some of the examples to make this concrete. Imagine you have two separate qubits. The first qubit is in a balanced superposition between 0 and 1, and the second qubit is definitely in the state 0. When we combine these, the first qubit superposition spreads across the second qubit state. The result is a superposition of two possibilities. First qubit is 0, second is 0, written as 0, 0. And the first qubit is 1, second is 0, written as 1, 0. Notice that we only have two terms in this superposition, not four, because the second qubit was not in superposition to begin with. Now let's try a more complex sample. Suppose both qubits are in a balanced superposition independently at this moment. The first qubit is equally 0 and 1, and so is the second. When we combine them, we get all four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1, each with equal probability. This is an example of a separable state. We can still think of the qubits as having individual identities. However, as we all see the next slides, not all multi-qubit states can be broken down this way. Some states are entangled, meaning the qubits are so intertwined that you can't describe them separately. This is where things get really quantum mechanical. Now we arrive at what might be the most bizarre and fascinating phenomenon in all of quantum physics, that is entanglement. When two qubits become entangled, they form a single quantum system that can't be described by looking at each qubit separately. They become so deeply connected that measuring one qubit instantly affects the other, no matter how far apart they are. This phenomenon bothered Einstein so much that he spent years trying to prove it couldn't be real, calling it spooky action at a distance. But experiments have proven that entanglement is absolutely real. Let me be clear by giving you a concrete example using what is called a Bell state, one of the most famous types of entangled states. Imagine we have two qubits in a special entangled state where they are always measured as the same value. Before measurement, we can't say whether each qubit is Q0 or 1. They are in superposition, but here is the weird part. The moment you measure the first qubit and get, say, 0, the second qubit instantly becomes 0 as well, even if it is on the other side of the galaxy. If you measure the first qubit and get 1, the second instantly becomes 1. The correlation is perfect and instantaneous. Think of it like having two magic coins. You give one coin to a friend who travels to Mars and keep the other coin on Earth. When you flip the coin with your coin and it lands on head, your friend's coin will always land on heads too. When yours lands on tails, their lands on tail as well. But here's the crucial quantum part. Before you flip them, neither coin is heads or tails. They are in a superposition. The measurement does not reveal a pre-existing hidden value. It creates a correlation instantaneously. This is fundamentally different from classical correlation, and it has been verified in countless experiments. Entanglement is real, it is weird, and it is incredibly useful in quantum computing. So why entanglement is so strange? Let's dig deeper into what makes entanglement so puzzling and powerful. The first question many people ask is, if measuring one qubit instantly affects another qubit far away, doesn't this follow a faster than light communication? The answer is no. And understanding why teaches us something profound about quantum mechanics. While the correlation is instantaneous, you can't control what results you get when you measure your qubit. It is random. So you can't send a message by choosing to make the other person's qubit be 0 or 1. You can only see that your random results are correlated with their random results when they compared the notes later. So another puzzle is how the qubits know what to do. If there is no signal passing between them, how does the second qubit know to become 0 when the first is measured to 0? The answer challenges our intuitions about reality itself. Because before measurement, the two qubits don't have definite individual states. The entangled pair forms a single quantum system described by one wave function. When you measure one qubit, you're really measuring the entire system, and this measurement collapses the whole wave function, not just the part near you. This has been tested by physicists over and over, including experiments that rule out any possible hidden information the particles might have agreed upon beforehand. Despite being strange, entanglement has incredible particle as well as practical applications that are being used today. Quantum key distribution, or QKD, uses entanglement to create encryption keys that are probably secure. Any eavesdropper trying to intercept the key would disturb the entanglement and be detected immediately. Scientists have also achieved quantum teleportation, where they transfer quantum information from one location to another using entanglement and classical communication. In further quantum networks, entanglement will allow quantum computers to be linked together across vast distances. What once seemed like a philosophical puzzle is now becoming a practical technology. Decoherence. Now let's discuss the biggest practical challenge facing quantum computing: decoherence. While entanglement and superposition give quantum computers their power, these quantum properties are extremely fragile. Decoherence is the process by which quantum systems interact with their environment and lose their quantum characteristics, essentially becoming classical. It is like trying to maintain perfect silence in a noisy room. Any interaction with the outside world disrupts the delicate quantum state. To understand decoherence, think about a beautiful soap bubble floating in the air. It is an intricate structure with rainbow patterns created by light interference, but touch it with your finger and pop it, it's gone instantly. Qubits are similar. They exist in delicate superposition states, but any interaction with the environment A stray photon, a vibration, a fluctuation in temperature can collapse the superposition. Once decoherence occurs, the qubit stops behaving quantum mechanically. It becomes just a regular bit, losing all these special properties that make quantum computing powerful. What causes decoherence? Many things. Thermal energy from heat makes atoms jiggle around, disrupting quantum states. Electromagnetic radiation, radio waves, light, cosmic rays, and can interact with qubits. Even the act of measuring requires some interaction, which is why measurement collapses quantum states. Vibrations from the floor, magnetic fields from nearby equipment, and even the quantum vacuum itself all contribute to decoherence. This is why quantum computers must be so carefully isolated from their environment. The in quantum computing is not just to build more qubits, but to build qubits that stay quantum long enough to perform useful calculations. Given how fragile qubits are, you might wonder how we manage to build quantum computers at all. The answer involves extreme engineering. Most current quantum computers operate at temperatures just a tiny fraction of a degree above absolute zero, about 0.015 degrees Kelvin. To put this in perspective, outer space is about 3 degrees Kelvin, so those qubits are roughly 100 times colder than the vacuum of space. This requires massive dilution refrigerators that look like giant golden chandeliers with multiple cooling stages that gradually bring the temperature down. But extreme cold is just the beginning. Quantum computers must be isolated from virtually all environmental interference. They are placed in vacuum chambers to eliminate air molecules that might bump into qubits. They are surrounded by layers of electromagnetic shielding to block out radio waves, magnetic fields, and other radiation. The entire apparatus sits on vibration isolation system like shock absorbers to prevent floor vibrations from disturbing the qubits. Some facilities even shield against cosmic rays from space. All of this infrastructure is needed just to give qubits a chance to maintain their quantum properties for few microseconds to milliseconds. This brings us to another major challenge: time limits. Even with all this isolation, qubits don't stay quantum forever. They have what is called coherence time, typically between a few microseconds and few milliseconds, depending on the qubit technology. This means we have to complete all our quantum calculations within this tiny window before decoherence destroys our quantum state. It is like having a computer that crashes and loses all its memory every few thousandths of a second. As we add more qubits and try to build larger quantum computers, we create more opportunities for decoherence to creep in. The scalability challenge is one of the main reasons why today's quantum computers are still limited to relatively few qubits. Now that we have understood the qubits and their challenges, let's learn how we actually manipulate them to perform calculations. This is where quantum gates come in. Just as classical computers use logic gates and or not and so on to process bits, quantum computers use quantum gates to process qubits, but quantum gates are fundamentally different from classical gates because they must preserve the quantum properties of superposition and entanglement while transforming the quantum state. Think of quantum gate as a precisely controlled operation that rotates the qubit state on the block sphere or create correlations between qubits. So each gate is like a specific button you can press that changes the quantum state in a well defined way. These gates are implemented physically using carefully timed pulses of microwaves, lasers, or other means depending on the type of qubit technology being used. The precision required is extraordinary. Gates must be accurate to better than 99.9% of the use and to be useful in quantum computing. Quantum gates have some special properties that classical gates don't have. First, they are reversible. For every quantum gate, there is another gate that undoes its operation. This is fundamentally different from classical logic, where the gates like AND as well as OR destroy information and can't be reversed. Second, quantum gates are unitary, which is a mathematical term meaning they preserve the total probability of all outcomes. Essentially, they conserve quantum information. Finally, quantum gates preserve superposition. If you apply a gate to a qubit in superposition, you get a superposition of the results. These properties make quantum gates the perfect tools for quantum computing. The polygate's basic operations. Let us start with three of the most fundamental quantum gates, called the polygates named after physicist Wolfgang Pauli. These are the quantum analogues of basic bit operations but with quantum twists. The first is the X gate, also called as bit flop gate or the quantum NOT gate. It does exactly what you would expect. It flips a qubit from state 0 to state 1 and from state 1 to state 0. If you apply the X gate to a qubit in superposition, it swaps the 0 and 1 components. On the Bloch sphere, this is 180 degrees rotation around the horizontal x-axis. The Y gate is similar to X gate in that it flips the qubit, but it additionally changes the phase in a complex way. Don't worry about mathematical details. Just know that the Y gate is like an X gate combined with phase shift. It's less intuitive than the X gate, but it is still fundamental to quantum computing. On a Bloch sphere, it represents 180 degrees rotation around the y-axis, which points towards U. The Z gate is particularly interesting because it does not flip the bit at all. Instead, it performs what is called a phase flip. It leaves state 0 completely unchanged, but it flips the sign of state 1. You might think this does not do anything useful since the probabilities don't change, but remember that phases are crucial for quantum interference. The Z gate is essentially for many quantum algorithms that rely on phase-based interference. On a Bloch sphere, it is 180 degrees rotation around the vertical z-axis. Together, these three polygates, along with the identity gate, which does nothing, form a complete basis of describing single qubit operations. Let me rephrase. If I had to choose the single most important gate in quantum computing, it would be the Hadamard gate. This gate is the primary tool for creating superposition from definite states, and it appears in almost every quantum algorithm ever designed. The Hadamard gate, named after mathematician Jacques Hadamard, takes a qubit that is in a definite state and puts it into a perfect 50-50 superposition. Let us see exactly how this works. If you start with a qubit in state 0 and apply a Hadamard gate, you get an equal superposition of 0 and 1 with a positive relationship between them. This is the pulse state we mentioned earlier. If you start with state 1 and apply a Hadamard gate, you get an equal superposition 2. But with a negative relationship, the minus state, which makes the Hadamard gate special, is that it's self-inverse. If you apply it twice, you get back to where you started. Apply Hadamard to 0, you get plus. Apply Hadamard to plus, you get back to 0. This reversibility is crucial for many quantum algorithms. On a Bloch sphere, the Hadamard gate rotates states from the poles definite 0 or 1 to the equator superposition, or vice versa. More technically, it is a combination of rotations that swaps the computational basics with the superposition basis. The Hadamard gate is how we unlock quantum parallelism. By applying Hadamard gates to multiple qubits that start in 0, we can create superposition for all possible bit strings at once. For example, applying Hadamard to 10 qubits creates superposition of all 1024 possible 10-bit numbers simultaneously. This is foundation of quantum computing's power. Now let's discuss phase gates, which might seem less dramatic than gates that flip bits but are absolutely essential for quantum computing. Phase gates don't change the probability of measuring 0 or 1, but they change the phase, the wave-like property that determines how quantum states interfere with each other. To understand why this matters, remember the quantum algorithms work by using interference to amplify correct answers and cancel out wrong answers. Phase gates are the tools we use to set up these interference patterns. The S gate, sometimes called the phase gate, adds a 90-degree phase shift to state 1 while leaving state 0 unchanged. Think of it like turning a wave by a quarter circle. The capital S gate does not look like it does much if you measure immediately afterward, but it sets up the state for future interference. The capital T gate is similar but more subtle. It adds a 45-degree phase shift. These specific phase angles are not arbitrary. They are chosen because of capital S and capital T gates combined with a Hadamard and C0 gates form a universal set that can approximate any quantum operation. To visualize phase gates on a Bloch sphere, imagine the sphere rotating around its vertical axis. The north pole, state 0, stays in place, but every other point on the sphere rotates around this axis. A full 360-degree rotation would bring you back to where you started, which is why phase gates can be applied multiple times to create precise phase shifts. For those interested in the wave analogy, phase determines when the peaks and troughs of a quantum state occur. When you combine quantum states, waves with the same phase reinforce each other. Constructive interference, while waves with opposite phases cancel out destructive interference. Phase gates give us precise control over these interference patterns. While gates like Hadamard and Pauli gates move qubits between specific discrete states, rotation gates give us smooth, continuous control over qubit states. These gates allow us to rotate a qubit state on the Bloch sphere by any angle we choose, not just fixed amounts like 90 or 180 degrees. This precision is crucial for many quantum algorithms, and for preparing specific quantum states. Think of discrete gates as being like the gears in a car. You can shift to first, second, or third gear, while rotation gates are like having the continuously variable transmission that can take any ratio. There are three types of rotation gates corresponding to rotation around the three axes of Bloch's sphere. The Rx, capital R, small x gate rotates around the horizontal axis, like rotating a globe around its equator line. The capital R, small y gate rotates around the y-axis, like tilting the globe toward forward or backward toward you. The capital R small z gate rotates around the vertical z axis like spinning a globe on its stand. Each of these rotations can be performed by any angle. You could rotate by 30 degrees, 17 degrees, or any other amount you need. Why do we need such precise control? Because in quantum computing, we often need to prepare very specific initial state for our algorithms, or we need to implement gates that are not in our standard set. With rotation gates, we can place a qubit at any point on the Bloch sphere with incredible precision. In fact, a powerful mathematical result tells us that any single qubit operation can be decomposed into a sequence of three rotations, one around z, one around y, and another around z. This means that which rotation gates we have complete control over single qubits. Combined with multiple multi-qubit gates like C naught, capital C naught, we can implement any quantum operation whatsoever. Now we move from single qubit gates to multi-qubit gates, and the most important of these is the C naught gate. The controlled naught, C stands for controlled naught gate. This gate operates on two qubits, one called the control qubit and one called the target qubit. The rule is simple. If the control qubit is 0, do nothing to the target. If the control qubit is 1, flip the target qubit. While this might sound straightforward, the C naught gate is absolutely crucial because it is the primary tool for creating entanglement between qubits. Let's work through some examples to see how C naught works. Suppose both qubits start in state 0, giving us a combined state 0, 0. The control qubit is 0, so C naught does nothing. We stay in state 0, 0. Now suppose the first qubit is 0 and the second is 1, giving us the state 0, 1. Again, the control is 0, so nothing happens and we stay in 0, 1. But if we start with state 1, 0, the control qubit is 1. So C naught flips the target from 0 to 1, giving us 1, 1. And if we start with 1, 1, the control is 1, and C naught flips the target from 1 to 0, giving us 1, 0 state. These rules are simple when the qubits are in definite states. The magic happens when the control qubit is in superposition. Remember our Bell state circuit from earlier discussions? We start with both qubits in state 0, apply a Hadamard gate to the first qubit to create superposition, and then apply C naught. Before C naught, the state is first qubit is equally 0 and 1. Second qubit is definitely 0. After C naught, when the first qubit is 0, the second stays 0, giving us 0, 0. And when first qubit is 1, the second flips is 1, giving us 1, 1. The result is perfect entangled state and equal superposition of 0, 0 and 1, 1 with no 0, 1 or 1, 0 terms. This is how C naught creates entanglement, and it is why this gate is so fundamental in quantum computing. This gate creates entanglement when the control qubit is in superposition. Beyond C0, there are several other multi-qubit gates that are useful in quantum computing. The swap gate is one of the simplest to understand. It exchanges two qubits. If you have one qubit in state 0 and another in state 1, swap will flip them so the first is now 1 and the second is 0. This might seem trivial, but in actual quantum computers, not every qubit can directly interact with every other qubit. Swap gates allow us to move quantum information around, though this comes at a cost because it takes multiple steps and introduces opportunities for errors. So, in reality, the language of quantum computing is reading quantum circuits. Just as electrical engineers use circuit diagrams to represent classic circuits, quantum computer scientists use quantum circuit diagrams to represent quantum algorithms. Learning to read these diagrams is essential for understanding quantum computing. Let's go through the notation step by step. A quantum circuit is drawn with horizontal lines where each line represents one qubit. Time flows from left to right, just like reading English text. As you follow a line through left to right, you see the sequence of operations applied to the qubit. Single qubit gates are represented by boxes or specific symbols on a qubit's line. You might see a box labeled H for a Hadamard gate, X for a poly X gate, or other symbols for different gates. These boxes tell you that at that moment in time, that specific gate is applied to that specific qubit. Multiple gates can appear on the same qubit's line, showing the sequence of operations. The key is to read them from left to right to see what happens to each qubit over time. Multi-qubit gates use vertical connections between qubit lines. The C0 gate is drawn with a dot on the control qubit line and circle on the plus sign on the target qubit's line with the vertical line connecting them. This shows that these two qubits interact at this moment. Some circuits also show measurement symbols, usually drawn as boxes with a meter or gauge inside. After measurement symbol, the qubit is no longer in superposition. It is definitely 0 or 1. By learning to read these diagrams, you can understand complex quantum algorithms at a glance, seeing how qubits are prepared, manipulated, entangled, and measured to perform quantum computations. Let's put everything together and build a complete quantum circuit from scratch. Our goal is to create an entangled pair of qubits, specifically one of those Bell states we discussed earlier. This circuit is simple but profound. It is the foundation for quantum teleportation, quantum cryptography, and many other quantum protocols. We'll need just two gates, one Hadamard and one C0. Let's walk through this step by step. We start with two qubits, both in the state 0. You can think of this as our initial state 0, 0. The first operation is to apply a Hadamard gate to the first qubit, leaving the second qubit alone. After the Hadamard gate, the first qubit is in equal superposition of 0 and 1, while the second qubit is still definitely 0. Our state is now first qubit is 0 and second is 0 plus. First qubit is 1 and second q is 0. In notation, this would be written as superposition of 0, 0 and 1, 0, each with equal probability. Now comes the crucial step. We apply a C0 gate with the first qubit as control and the second as target. Remember the rules. If control is 0, do nothing to target. If control is 1, flip the target. In our superposition, half of the time, first qubit is 0, so the second stays 0, giving us 0, 0. And half time, the first qubit is 1, so the second flips to 1, giving us 1, 1. The result is an entangled state, perfect superposition of 0, 0 and 1, 1 with no 0, 1 or 1, 0 terms. The qubits are now correlated. Measure one and you instantly know what other will be. The simple circuit, just two gates, create one of the most mysterious phenomena in physics. Now let's look at more complex and fascinating circuit, quantum teleportation. Despite a science fiction name, this does not teleport matter. It teleports quantum information from one location to another. Imagine you have an unknown quantum state that you want to send to someone far away. You can't just measure it and tell them the result because measurement destroys the superposition. And quantum mechanics has no cloning theorem that say you can't make a perfect copy of an unknown quantum state. So how do you send it? The answer is quantum teleportation. I would suggest you to look at the slide very carefully. I'll give you a pause so you can watch it and try to understand, because this is the whole concept that we will discuss in depth in our later discussions. An important theoretical question in quantum computing is how many different types of gates do we need? Can we build any possible quantum operations with just a small set of gates, or do we need infinitely many different gates? The answer is encouraging. Just a few gates are enough. We call a set of gates universal if you can use combinations of these gates to approximate any quantum operation to any desired accuracy. This is similar to how you can build any classical circuit using just NAND gates, and how you can mix any color using just red, blue, and yellow paint. So the theorem is any complex quantum operation can be broken down into a sequence of simple gates from a universal set. Think of it like building a Lego operation just using few types of basic bricks. That's the main understanding. Now let's be realistic about where quantum computing stands today. While we have made tremendous progress, we are still in early stages of this technology. Think of where classical computers were in the 1950s. Today, quantum computers can do things impossible for classical computers, but they are not yet practical for most real-world problems. Understanding these limitations helps us appreciate both how far we have come and how far we still have to go. The first major limitation is qubit count. Current state of the art quantum computer have been between 50 and 1,000 qubits depending on the technology. That might sound like a lot, but solve genuinely useful problems like breaking modern encryption or simulating large molecules for drug discovery. We'll need millions of qubits. Why so many? Because we need error correction due to the decoherence phenomena that we have discussed and gate errors. Current qubits make mistakes. To create one reliable logical qubit that does not make errors, we might need 1,000 or more physical qubits working together to detect the correct errors. This overhead is enormous, and it is one of the main challenges facing the field. Error rates are another major issue. Even the best quantum gates fail about 0.1% to 1% of the time. That might sound It might not sound like much, but if you need to perform thousands of gate operations for a complex algorithm, these errors add up quickly and destroy your result. Then there is a coherence time problem. Qubits only maintain their quantum properties for microseconds to milliseconds, limiting how long the complex our calculation can be. Finally, there's a cost. Quantum computers require extreme cooling, precise control systems, and sophisticated error correction. Each of these challenges is being actively researched and progress is being made. But we are probably still a decade or more away from quantum computers that can tackle practical problems better than classical computers for a wide range of applications. Let's wrap up by reviewing the key concepts we have covered today. We started with qubit, the fundamental unit of quantum information, unlike socially socialized information, which is classical bits that are definitely 0 or 1. Qubits can exist in superposition, genuinely being both 0 and 1 at the same time until measured. We learned to visualize qubit states using a block sphere, where every point on the sphere surface represents a possible quantum state. We discovered that multiple qubits can represent exponentially many states simultaneously, giving quantum computers their potential power. We then explored quantum entanglement, perhaps the strangest phenomenon in all of the physics. Entangled qubits become so deeply connected that measuring one instantly affects the other, regardless of distance. This is not science fiction, it is real, proven, and being used in quantum technologies today. We also discussed decoherence, the process by which quantum states are destroyed by environmental interactions, and learned why building quantum computers require extreme isolation and cooling to keep qubits quantum long enough to perform calculations. In the second half, we actually dove into quantum gates and circuits. We learned about single qubit gates like Hadamard, polygates, and phase gates, which manipulate individual qubits. We explored multi-qubit gates like capital C naught that create entanglement and correlations. We discovered that just a few gates from a universal set capable of approximating any quantum operation. Finally, we saw that you can program quantum computers today using free online tools and real quantum hardware. Quantum computing is moving from theoretical physics labs to practical engineering reality. While significant challenges remain, the progress is accelerating, and you have been in a field where you're learning these concepts at an exciting time in the development of this revolutionary technology. So you're part of the history. Think of you for attention. In my opinion, think of you as one of the founding people in quantum computing theory. So thank you so much for your attention. I hope you're excited about quantum computing as I am, and we will get on touch in the next lecture. Happy learning.